All right then. So we swapped X and Y, and now we're just going to go do some basic algebra. Um, so the first thing I did is I multiplied everything by three. You hang around with me long enough, you know that that's just a thing, right? If the variable that we're trying to solve for has a fraction attached to it, it's a good idea to eliminate that fraction.
We don't subtract.
You could subtract four first, or you can subtract four after. I could go literally one day one way and the next day the other way. So that's going to be inconsequential in this case. So if you subtracted four, you can still multiply by three. I just figured I'd get it done. So if I multiplied by three, I just get 3x equals 12 minus 2y. And then from here, it's just, no fractions, smooth sailing. So the way I like to do my algebra um, is I like to write my next step like this. And then you might think that, I don't know, you may not like to do it like this, but I moved, I think I moved everyone except the 12, right? I've got a little bit of a thing, a disorder, if you will, about loving to always have the Y on the left. And so I try not to always impose that on my students, but I really like having Y on the left. So I moved the minus 2Y over, made it positive, moved the 3x over, made it negative, and then just left the 12. And then we got to divide by two and we'll be done. So we get Y equals negative 3 halves of X plus 6. So what I'm going to ask of you starting today is that you not write your answer like this, and you'll see this if and when you ever decide to look at my answers that I'll post later. But we don't write our inverses like this. We write them like this. F to the negative first power. I believe that came up on the first day that we did inverses, and I don't know why I wrote that so funny. I'm going to rewrite that. So it's F inverse of X equals negative 3 halves of X plus 6. Okay. So what we have so far is we have two functions. We have a function that was given to us originally, and we have a function that we actually just found on our own called the inverse. As you look through later on, my work, if you choose to, I tried to keep it so that you could see the separate graphs that we're about to do. So I tried to be consistent to always use green for the original function and red for the inverse function. Are we okay so far? Okay, so what we're going to do now is we're going to graph a couple of things. And these graphs are honestly just algebra one graphs. So a couple of straight lines is how we're going to start the day. So what I want to do first is graph the green. And I don't know if you're someone who uses colors or not, but if you are, today would be a great day to start using them because um, I want to be able to see the graphs. There's a thing going on later on that I want you to be able to see. And I found the colors. I originally did it in pencil, and I didn't like the way it looked with pencils. I like the colors, so whatever.
Or when you're going
Yeah, if you want to borrow one of my red pens, you can. There's also I don't know, but that sure looks like it could be a green pen. I have no idea if it is or not.
doesn't help if you have one.
Oh, it might be dead. Here's a blue one too. Roy.
And it is. It's like the
Teal. Um, so this one and the next one, I don't feel like we need to make a table of values. And I know that it's been a while since we've graphed straight lines, but you'll remember y equals mx plus b. So to graph the green function, I'm going to start with the y-intercept, which is at 4. In case you're a little bit rusty here, I'll be courteous and write this the way you might more recognize it. Y equals negative 2/3 of x plus 4. That's the way we would usually see it in algebra land. So then we remember, ooh, the y-intercept is 4. So I'm going to start this graph at 4. And then it has a slope of what?
down to
Down and left would actually make it go positive. So we want to make sure, yeah, if it's a negative slope, you spent your negatives by going down, and now you can't use anymore. So you got to go right 3. So this would have been an activity that we would have done years ago together back in Algebra 1 class. And then what you want to do is just graph a boatload of points. And then if you don't have a ruler yet, you probably want to grab one from over there and then make a line. Always remember that your lines should go, as a general rule, they should protrude out both sides of the grid. Is that a funny word? Protrude. Any issues with the green line? All right, let's talk about the red line. So the one I circled in red, where does that graph start? Up 6. It's okay. And then the slope is what? Down 3, right 2. And I think, yeah, never mind. I'll just deal with this in a second. So down 1, 2, 3, right 2. Down 1, 2, 3, right 2. Down 1, 2, 3, right 2. And the reason I gave you this explanation years ago, but the reason why it's always a good practice to plot a lot of points is because if you connect dots that are far apart, then your ruler doesn't get off kilter. Sometimes if we only do like 2 points and we think we're going through the points, the line actually can get off by quite a bit when you get a few inches away from center mass. So then we're going to grab our rulers. And we're going to make a line that goes through the points like this. So you don't probably see it yet, and I think I've alluded to this multiple times, but these two graphs they're in an inverse pattern. Does anyone recognize any sort of symmetry with them? Yeah, that won't certainly always be the case.
One of them, um, yeah, one of them goes down 2, one of them goes down 3,
I
right?
agree. Yeah, so the slopes are like kind of related in that way. Someone tried to teach this to me when I was 17, and I probably was resistant to it. So it would be easy for me to say, boy, I wish someone would have told me this. They probably did. I just probably wasn't listening. Here's the interesting thing about inverses. Do you remember what the first step is when we go to do an inverse? We switch them. So we basically take a y and we say, y, I need you to equal x, and x, I need you to equal y. Would you agree with that assessment? Okay, so let's have a little algebra 1 flashback here for a moment. If I asked you to graph the line y equals x, where would you start? At 0, and what is the slope? Good. So what I want you to do right now, what you just heard me say, I hope you realize the importance of this, is this line y equals x. It exists for a reason. Like it is the line about which y's and x's literally change places. It's one of those times where something honestly just almost defines itself. Why does this work? Because of that. When we find an inverse, we make y equal x and we make x equal y. So what we're going to do is we're going to take on this same graph and we're going to graph the line y equals x, which is this line right here. And this becomes the thing now. The thing is that this line should appear now in every single one of our problems because it is, I know you're not back reading the directions up above, but it says then sketch the line y equals x to show that they're actually reflections or inverses of each other. And you can now plainly see, maybe not yet if you're still catching up, but you can plainly see that every point on the green graph, if you reflect it perpendicularly straight across that purple mirror, has a counterpart on the other side of the mirror. That means that the red line and the green line are reflections of each other. The red line is a reflection of the green line and vice versa. So this is how we visually verify that two functions are in fact inverses of each other, is we graph y equals x, and we can go hot dog. Sometimes it helps to like turn your head a little bit or turn your paper, and you can actually see how those wings, those lines are symmetry or symmetric. So that is that, and that's our warm-up problem one. Do you have any issues with that? Okay, I do want to skip problem two. My teacher sense is telling me that now would not be the right time to talk about a domain restriction, so we're going to hop ahead to problem three. So let's get to the algebra portion of it first. And the algebra portion of it is I'm just going to find the inverse like a robot. And so to find the inverse, we're going to first switch x and y. And we're going to have x equals the cube root of negative y plus 3. What do we do now? Raise everything to the power of 3. The left side, if I raise it to the power of 3, we'll say x cubed. The right side, if I raise it to the power of 3, we'll just say what? Right. Now, again, I am a y on the left kind of guy, and I'm especially a y on the left kind of guy when I also get the benefit of moving a negative y and making it become positive. To me, that's like bonus, double bonus. So I'm going to move the y to the left and say y equals, and then I'm going to move the x cubed to the right, making it negative x cubed. And then the 3, again, is just going to sit and watch us screwing around. So please remember, don't leave your answer like y equals. I really want to get you trained into that idea of how do we write an inverse again?
F to the negative first power of x.
K. So we're going to write k to the negative first power. That's in math terms, that it literally says k inverse. K inverse of x equals this. Now, what I decided, and I feel really good about this choice, is much like we did the other day with the log functions yesterday and the day before, I don't want to talk about flips and stretches and that. I want to get away from that for a while. And if you look at my notes later on, you'll see this. We're going to make tables. So I'm going to make one table. You'll see what I mean in just a second for that green one. And we're going to make another table for that red one. And I'll show you how easy this is to do. And listen, of all the things we teach you, this is one I want you to take. This is a gift from me to you. I said this before. If you ever come up against a graph and you just don't remember what it looks like, make a table, do what we're about to do, and you can piece together a lot of puzzles this way. It doesn't reveal everything, but it's sometimes a good jumping off point. So my table is going to be, I'm going to zoom out just a little bit so I can fit a little bit more on here. So I'm going to make a table that looks like this. I'm going to write x on the left side, and I'm going to write k of x on the right side. And God, I hope this isn't confusing. This should be anything but confusing. This should feel almost like a relief. Like this is old school graphing. If I want to know how to make a graph, I just plug in x's and get out y's, plug in x's and get out y's. So going back up to the function at the top that's in the green bubble, what would be a good place to start? Choose wisely. Don't just pick some random number out of your kabushker. Because you better be thinking, I I don't like that.
Extra negative 5.
I don't like that. What do we want? Let me zoom in real close. And I'm going to zoom back out. What do we want that to be? Something that's cube rootable. So if you give me a number and inside there's a 9, I'm going to say no thank you because 9's not cube rootable. If you give me a 2, I'm not interested. What are the numbers that are cube rootable?
No, 8.
8 is good. What else? 1 is good. 0 works. 27 works, but we're probably not going to be able to stretch ourselves that thin. But you're right. You're right. So what I'm thinking is, can I make the numbers inside of that egg, inside of that root, equal interesting numbers to me? -8, -1, 0, 1, and 8. Every one of those 5 purple numbers is cube rootable. Because remember, cube roots don't give a hoot about signs. Cube root of -8 is doable. Square root, different conversation, right? So those are not the values that I'm going to put into my table. They are, however, the values that are going to sort of guide my decision making. So what could I put in place of x to make what's inside the root equal -8? I think 11 is a good choice. If you put 11 where the x is, and there's already a negative built in the front, that's -11 plus 3, which last I checked is in fact -8. And what's the cube root of -8? -2. So we have a point on our curve. We put in 11, we get out a -2. And I realize that the graph doesn't quite go to 11, but honestly, there'll be times throughout this where you can actually stretch to 11 and 12, just using some estimation. Like 11 ought to be pretty easy to figure out. Okay. So I can check -8 off. What can I put in place of x to make it equal -1? Correct. If x itself is 4, then it's -4. And -4 plus 3 is -1. And the cube root of -1 is another -1.
Shouldn't that be a 4?
Yeah.
-4, -1.
Negative 4.
I knew that. I was testing you guys. Yeah, yeah, okay, whatever. Thanks, guys. And what else? So I can check this off my list. What else? Uh, I think I want it to be a 3. Here, I'll write it down this time so I don't get ahead of myself. 3. So if it's a 3, then that's -3 plus 0, which is 0, and the cube root of 0 is 0. So you see, this is my new tactic for you guys. I feel like you're going to like graphing this way better than stretching and flipping and pulling. And this, what's great about this method of making a table is that it works for anything. It's rad, like anything. So how can we make what's inside equal a 1? If x is a 2, then it actually says -2 plus 3. So if x is 2, -2 plus 3 is 1, cube root of 1 is 1. And then lastly, how can I make the inside equal an 8?
-5.
Yes. If x itself is a -5, and then you use the built-in negative with it, that becomes a +5 plus 3 is 8. So I want a -5, and then when I plug that in, I get 2. With me so far? Now, what we're going to do is right next to it, we're going to make another table of values. And this one, you might have guessed what it's going to be called. But when we build it, we're going to put x on the left. What are we going to put on the right? Nope.
K is negative first power.
K inverse of x. Very good. So what I'm trying to get us to do here, I got to choose my pathways when I'm trying to guide you guys down this dangerous road. I think the best way for us to graph a function and its inverse is just to go old school. Find some points, connect the dots, and let the graph happen. So when we think about K inverse of x, that's the one that's in the red egg. You don't have to be quite as picky with these ones, but you still should be selective. What's a good x? We're going right here, by the way, where these arrows are pointing, in case you didn't figure that out. What'd you say? I'll take 1. I think 1 is reasonable because if I put 1, and I'm going to circle this for you. In fact, I'm going to put a funny, like a weird purple blobby jelly bean shape around it. That little purple jelly bean blob shape is the first thing we're going to have to do every time, right? So if you put 1 in the little purple jelly bean, what's 1 cubed? 1, and then you stick the negative on it, and it's -1, and -1 plus 3 is, so we have a point. It's going to be a logical question you're going to want to ask here. Not all of you, but a couple of you in particular here within the next couple of minutes, and I'll address it when the time comes. Give me another good x. I'll take -1. So again, if your basic skills suck, well, I'm so sorry, but this stuff like this will be harder for you. So if you put -1 inside the little purple blob, what's -1 to the third? What is -1 to the third? It is -1 because it's a negative times himself. That's 3 negatives, which makes -1. So if the purple blob equals -1, but then you put the negative in front on it, what's the negative of a -1? And then 1 plus 3 is 4. Let's try 2. Again, we don't have to be so picky because we're not trying to make things that are like cube rootable. We just don't want to pick something stupid like 3 or 4. Because what happens if I pick those?
Numbers.
Big number.
The numbers get too big. And it's not like it's against the law. It's just doesn't work with what the real estate that we have here. So let's try 2. If you put 2 in the funny purple blob, what's 2 cubed? 8. Stick the negative on it. You get -8 plus 3 is. Has anyone noticed anything yet? All right, I'll take that as a no. There you go. Good. Yes. And so let's put in a 0. And if you put 0 in the purple blob, 0 cubed is 0. The negative of 0 is still frickin' 0, and 0 plus 3 is 3. And I think the last one that we could reasonably expect would be -2. Right. So -2, if you put it in the purple blob, -2 cubed is -8. Stick the other negative on it, you get +8. 8 plus 3 is 11. And by now, I'm almost certain that you've made the connection that all of the points in the table on the right are the flip-flop of the points on the left, which of course begs the question then, do I really have to do all that math? What do you think the answer is?
Maybe 1.
The answer is very much 100% yes. Because here's the deal. Let's just say that something has gone wrong with the green table. Could it? Maybe us being humans, like me earlier when I wrote the wrong number down. Could something be wrong with the green table? Right. And if I use the green table and just flip all the points around without doing the math, I run the risk of using a broken tool, which then creates a broken answer, and the whole thing goes downhill. So I am telling you, as a guy that will not lie to you, that doesn't make you do extra work for nothing, that you need to do the work in both tables to verify that they're working legitimately. It feels good when the 2 and the 11 or the -2 and the 11 match the backwards of the 11 and the -2, but I didn't just put an 11 here because I wanted it there. I put it there when it was supposed to be there. And then I can pat myself on the back and see that for every point over here, there's a match over here. You see how those are inverse points? You see how those are inverse points, inverse points, inverse points, inverse points. See it? So let's go graph. Let's graph K of X first, and I'll use green dots for K of X. So we're going to go to the graph and we're going to plot all of the points from the K of X table. That's the one on the left. And so for 11, -2, I just figured it would be right about here. Eh? Close enough, huh? And with these annoying QB graphs, honestly, that's going to be annoying either way. You could be off by 1/4 of an inch and it'll still work. So 4, -1 is right here. 3, 0 is right here. 2, 1 is right here. And -5, 2 is right here. And then if we wanted to go further left, we actually could to get up there, but I think this is sufficient. We'd have to go pretty dang far. So good. So now, of course, as you know, if you're good at math, the hardest part about any of this is trying to make the graphs look decent. It takes some time. It takes some doing. So I'm going to just try and I'll just make an absolute mess out of this stinking thing. Here it goes. It's coming in. Whoa. I would say that that's pretty butt ugly, but it'll do. Got it? All right, now let's plot the points in K inverse of X table. That's the second table. And I'll switch colors for this one. So I assume you're doing all of this as I'm up here yip-yapping. So to get to -211, again, I have to freestyle a little bit, but not much. I just have to go up to -2 up to 10, and then just kind of put my point where I think I'm at about 1 unit above, which, good enough. And then you sketch the curve, try to do it. Oh, God. Oh, nope, that's bad. These look much better on my notes on paper. Just saying. So finally, on every problem like this, your uh, final task, unless you want to do it before this, is to sketch the line y equals x. On every single problem, you have to graph the line y equals x. And if things have gone according to plan, your graph should look like the one on the left and the one on the right are mirrors of each other. And if you haven't figured out what I'm talking about yet, like that's totally possible, right? Like you're like, I still have no idea what you're talking about, you meathead. Take a look at like this point right here and this point right here. You see how they're mirror reflections of each other? That's when we know we're doing something right. When every point on the red graph can be mirrored to find its mate in the green graph, like this point and this point, this point, this point. Isn't it rad? That's when you know you've graphed a couple of inverses correctly when you get that super sweet symmetric vibe.
I think the easiest way to find out is just look at the line, like on the green one, it goes through x equals 3.
Yep.
And the red one goes through 1.
100%. And these you're going to make probably 5 or 6 different little connections and shortcutty thought processes like that as you go through and work these. You see that, yes, you're exactly right. Like a 0, 3 is the same as a 3, 0. And, a 5, 3 is the same as a -3, -5. It's really cool stuff. Let's do this last one, number 4, and then we'll save. Do you want to do 2 or 4? 4 is fine. Let's do 4. And then we'll come back to 2 on Monday. So we got ourselves your favorite kind of graph here, an exponential. And first job is to find the inverse. So we're going to swap our variables and we're going to say x equals 2. We did a whole worksheet of this, if I recall correctly. Are you throwing gang signs over there? Wow. We did that on purpose. Because it has a domain restriction that I didn't think maybe would be the right thing to talk about today. So that was by design. So here we go. What do we do first? Add 4 to both sides. So we wind up getting x plus 4 equals 2 to the y minus 2. Next.
Yeah.
God, I was thinking to myself, I wonder if anyone's going to say reverse water cycle. And then I was like, oh, like the music from, oh. Yes, we have to hit it with the reverse water cycle. So what this is going to become is log base 2 of x plus 4 equals y minus 2. And then we're almost there, right? We got to get the y by itself. There's no need to write the y equals step if you know you're just going to change it to the inverse notation. So if it were me personally, I would just jump right in and say j inverse of x is equal to log base 2 of x plus 4 plus 2. You would agree that it feels like redundant if we keep writing y and then the other notation. So just skip it. So we find ourselves now in the exact same position that we have on the last 2 problems, or at least the last 1 problem. And that is that I don't really feel like dealing with graphing these, talking about pulls and moves and stretches. If you like graphing that way, okay, you go. I think the table is my safest explanation. So on the left, I'm going to make a table for j of x. So this table is going to be called x on the left, j of, that pen is too fat. Hang on a second. X on the left, j of x on the right. That's just really a fancy math way of saying inputs on the left, outputs on the right. Yeah. So we're back up to the top function now, the one that's up at the top of the TV, up right next to the number 4 on your worksheet. What would be a good X for us to pick? I would accept 1, but 1's going to get some people confused, but I have to do it anyway. So here it goes. If I put 1 where X is, it'll say 2 to the 1 minus 2 minus 4. What's 1 minus 2? -1. So this is 2 to the power of -1 minus 4. What's 2 to the -1? And don't say -2. 1/2. Nice job. And what's 1/2 minus 4? Good. So if we pick what you said, Super Cooper, if we pick 1 for our X, we get -3.5 for our Y. Wasn't expecting that to be your first choice. What else would be a great choice for X?
-3.
Uh, Hold on a second. I need to color code for you guys, and I should do this all the time. We are on this function, the one with the green around it. Are we clear?
Yeah, I was looking at the wrong one.
I know you were. That's why I went up and drew green bubbles for you. So hold that thought. What else would be a good X? I like 2. 2's pretty friendly. If I put 2 in there, I don't need to show work for this one. This is stupid. If you put in the 0 or the 2, you get 2 to the power of 0, which is 1. Anything to the power of 0 is 1, and 1 minus 4 is okay. So these points are pretty close together because the exponential business hasn't started yet. We're still down by the asymptote. We're coming in for the landing here. It's going to start to get more exciting. It's not the right word as our x's get bigger. If x is 3, what's 3 minus 2 is 1, right? 2 to the 1 is 2. What's 2 minus 4? -2. Okay. Start to see it happening here soon. 4, put in 4 for x. What's 4 minus 2? 2 to the 2, 4 minus 4. Okay. Liftoff is about to commence. Let's do 5. 5 minus 2, 2 to the 3, 8 minus 4. And let's try one more. Let's press our luck. I think we can make it, almost make it. Put in 6 for x. What's 6 minus 2? What's 2 to the 4? 16 minus 4. Or 12. I'm going to go with 12. You do 10 if you want. I'm going to do 12. Might work either way. So here's the deal. Time flies when you're having fun. Your bell's going to ring in 31 seconds or 25 seconds. I know, right? So didn't make it, but we're gonna remember we're right there. We skipped problem 2 and we're right in the middle of problem 4. Got it? And we'll pick up this riveting conversation on Monday. Yeah. Hey, everybody say bye to Blair. Say it really loud.
Bye, bye.
Bye, Blair. That was not loud.
Thank you.
See ya.